Okay, guys, let's continue here. So this is the cause of motion, or basically we should say the cause of circular motion towards the center. Okay, so it is the x component of the normal force. It's equal to, because it is this one, right? So again, this is the vertical on the plane, or sorry, this is the vertical on just the normal vertical. This is the horizontal. The plane itself, or the curve itself, the road itself, is with an angle theta, and this is the normal to the surface, which is, you see, it's perpendicular to the surface itself. Okay, because this is the line of the surface. You see, this is the line of that ground, so this is the normal to that line. And in this example, or actually in the banked curves, the main difference that here the Fn is not on the y-axis, it's with an angle with respect to the y, so it has components. This is the y component and this is the x component. The y component is equal to the gravitational force, and the x component is the cause of the motion. It's in the same direction as the centripetal force, which is mv squared over r. And here, as we know, it is Fn cosine theta minus mg, that the summation of Fy is equal to 0. So we have two equations. One is this and the other is this. If we simply say that Fn cosine theta is equal mg, all right? And from here, Fn sine theta is equal mv squared over r. How to solve these two equations? This one and this one, let's say. Okay, these two equations. We can simply divide them over each other. Why we can divide them? If we divide them, we can cancel the Fn. All right. Again, what are we looking for? We are looking for the banking angle. Okay. So if we divide them, we can cancel the normal force, which is okay. Sine theta, cosine theta is equal to the right side mv over r, mv squared over r, divided by mg. You can see, first of all, Fn goes and the other is m cancel out. So we can see that sine over cosine is tan. Tan theta is equal v squared over r times g. All right. So the banking angle is equal to tan inverse of v squared over rg. Again, you can see that it does not depend on the mass of the car. It does not. If you remember also, the maximum speed to keep the car moving in a circular horizontal path without slipping was also independent on mass. It doesn't depend on the mass. Also, the banking angle, it doesn't depend on the mass of the vehicle. Okay? Of course, this is the maximum speed which can keep the car moving on that track without slipping. Okay? You can see that the angle depends, of course, on the speed of the car rather than the mass, the radius of the that circular path that we are moving, and the gravitational force. It's always there. G is always there. All right? I wouldn't memorize this one. Believe me, you can see how many formulas we are having so far. You can write them down. I have no problem. But you can see it's much better to understand the situation. Mainly you are doing summation of the forces along the x, which is the centripetal force, and along the y, which is equal to 0. And you get the equation out of this, the equation out of that, and you solve two equations. Okay? But it's, of course, a good idea to know how the formula will look like and what are the variables that the angle is depending on. So tan of the angle is proportionally depending on the square of the speed of the car divided by RG. All right? Okay. Now, so you see, this is the formula. The angle of bank. The angle of bank. Okay. Now, I want to solve an example. Let me see which example we can do today. We can, all right, actually, yes, example 5.7. There we go. There we go. If we finish this, that's great. So this is the banking angle. For a car traveling with a speed of v, so there is the speed of the car. Okay. It looks like we have an inclined plane, right? But there's a huge difference. The car, this is the cross section of a circular motion. The car, you see, car is coming towards you, or of that matter, it's going away from you. But the car is not moving on this or there. The car is not. This is the face of the car. You see, this is the face of the car. So it's not moving in here or there. Okay? So the motion of the car is towards the center, because you see the car is moving and it will go in a circular path. And this is at one point of that circular path. All right? So this is the normal. So this is the surface. This is the normal to the surface. This is the normal to the surface. And this is our normal gravitational force. This is our y. This is our x. You see? You see? Now, this is the acceleration. Earlier in the inclined plane, the acceleration used to be either here or there, صح? But we don't have this anymore. The acceleration, this car is going into a circular motion, so the acceleration is towards the center. All right? So simply, there is a curve of radius r, all right? And the speed of the car is v. Determine the formula. Okay, if he said determine the formula, it means you have to determine the formula. You cannot just plug it in. For the angle at which the road should be banked, this is a real question for engineers, that at which angle should the road be banked so no friction is required? Means, like, basically banking of the road itself will keep the car on the road. It's not the friction between the road and the car. All right? It's not, it doesn't depend on the friction between the road and the car to keep the car on the road. It is the angle, the choice of the proper angle, which will keep the car moving on the road into a circular motion. All right. So the formula. We have already derived the formula. I don't want to go through that again, but I can go through it for your sake to see how simple it is in a very quick way. This is the easy one because we don't have movement along the y. What are the forces along the y? It is the component of the Fn cosine theta minus mg is equal to 0, and summation of fx is equal ma centripetal. This is where the motion is going. What are the forces along the x-axis? It's simply the x component of the normal, sine theta is equal to mv square over r, and we get these two equations. From here, we remember that this is equal to mg, so we divide them over each other. Fn cosine theta divided by Fn sine theta is equal to mg over mv square over r. If you see, I flipped them by mistake. Not by mistake, just I didn't follow exactly. In the previous derivation, we started with the x, so I flipped them. It doesn't matter. Fn will go with Fn, m will go with n. Okay, we can flip those. Sine over cosine is tan, but don't forget to flip those. V square over R. Great. So what is the formula? Theta is equal to tan inverse of V square over RG. Alright? Okay. What is the angle for a rod which has a curve? Now he's giving me values. So the radius R is 50 meter with a speed of 50 kilometer per hour. You basically, and this is of course 9.8 meter per second square, you will plug them in here and you will find the angle. Before that, you have to convert your speed, right, into meter per second. So 1 kilometer is 1,000 meter, and 1 hour is 3,600 seconds. So this is equal to 14 meter per second, and you plug in that in the theta. Theta is, you plug in the number and you will just get the angle to be 22 degrees. All right, very good, very good. Alhamdulillah that we're done with this example. Now the last thing I want to mention in this chapter is, this is another actually example. Okay, there's a very different kind of motion here, and it is, you can find it always in the amusement parks, or even in, I mentioned that in Dubai Eye or Abu Dhabi Eye, London Eye, you know this. I think all of you have seen it. This is the wheel that, you know, it will be rotating vertically. You see, this is different now. All what we have studied was horizontal. A person, for example, with a rope and a ball at the end of the rope, and he's, you know, trying to rotate the ball in a horizontal circle. All right, not in a conical shape, in a horizontal circle. But here the movement is not like that. It is vertical movement. So I want you to know, and I want you to make sure to understand the difference. This is the wheel. The wheel is a vertical movement, all right? And it is a uniform circular motion, but there is the addition of gravity in it. Okay. I will not go through these kind of things now, but I want you just to understand what is going on in the wheel. In each situation, there is a normal and gravitational force, okay? Like even if you are at the top or at the bottom, you always have a gravitational force down, all right? It's always down, okay? And there is also normal from the surface on the object, okay? I will stop here. And I will see you in the next YouTube.